Hello everyone, I'm Rinku Dhiman, working as an assistant professor in electrical engineering department at RPIIT Technical and Medical Campus, Karnal. So today I'm going to discuss about the integral controller. In earlier lecture, I have discussed about the proportional and derivative controller. So this is the another version of controller, which is also based on the that is the integration of our error. So output will get the directly proportional to integration of our error. So we discuss about the integral controller in further slide. So integral controller have the constant ki, also called the integral constant. So I stand for integral. So k is basically nothing but proportionality constant. So integrating the above equation, actual controller output at any time t can be obtained by this equation. So PT is directly proportional to Ki integration 0 to T et dt and plus P0. So P0 is nothing but the controller output when integral actions start at T is equal to 0. So this is the time period because we know that the output of our controller at 0 error should not be 0. Right. So for that purpose, we will consider this P naught 0 over here, and otherwise PT is directly proportional to integration of our error, and the proportionality constant will be Ki. So this is the mathematical representation of our integral controller. So in the proportional controller mode, error reduces but can't go to 0. So that was the disadvantage of our proportional controller. Error will be reduced, but it will not be 0 at the 0 position all time. So it is finally produces an offset error. So if the error is not 0, so there will be some offset error, and it cannot be adapt the changing load condition. So if the load will be increased or decreased depending upon the application, so it can't be adopt that thing. So to avoid this problems, another control mode is often used in control system that is based on the history of the error. So we will consider that type of controller in that case, which output will depend upon the past value of our error, and this mode is called integral mode or reset action controller. So integral mode or reset controller action controller means the past value of error will be used to take an action by the controller. So in this type of controller, the value of controller output PT is changed at a rate which is directly proportional to escalating error signal, and that can be we can say that mathematically equal by this one. So the change in controller output, that is dpt by dt, is directly proportional to error, that is et. So directly proportional is equal to nothing but our constant ki, that is relating to error, and if we'll take the Laplace transform of this equation, then it will become dpt over dt ko we can write like s into ps. Ki will be constant, so it will be written this, and et will be written es. So we'll calculate the power from this equation, then we will get the Ki by S. So Ks will be divided over here. So then Ki by S and Es. So that is our transfer function of output power. So if we'll draw the block diagram for the integral controller, this will be look like this. So Es will be input and Ki by S will be the integral constant and Ps will be our output. So this is the complete structure of integral controller. So now we'll talk about the advantages of PI controller. Basically, it provides the better stability of the system. Like in a proportional or derivative controller, we will not get the stability as much as on the we can say that very clearly stable system over there. So next is its simple and directness. So basically it will provide the simplicity and directness to our applications. Then it is fully eliminates the steady state error. So offset is very less, or we can say that steady state error completely eliminated this. So if the error will be reduced over there, we will get the desired output, and have a good transient response in this system, and it stabilizes the controller gain as well. So these are the advantages of PI controller. If we'll talk about the disadvantages, it takes the long timer or longer time, we can say that, to stabilize the controller gain than the proportional controller gain. As the proportional gain and controller gain are fast, but this will give the more stable system and less error, so it will take the time to stabilize the integral controller gain. It suffer from only oscillation induced by the integral overshoot. So whenever there will be an integration action take place, so there will be a overshoot in the response of the system. Okay, so it requires excessive stabilization when the process has many energy element or dead time, we can say that. So it requires a long time for its stabilization. When there if we include the number of element in the system, or the number of process will be included in that. Thank you very much. This is all about the integral controller. Please stay tuned with us for more videos on the control system. Please like and subscribe our channel. Thank you.